Okay, good afternoon. Welcome back. I hope we enjoyed the snow day. So last time we had our quest. I've given the quest back. In general, the results on this quest were quite good. This was even stronger than our performance on the first quest. So if you did well, fantastic. If you have any questions about the quest, this particular one, I do have the answer key right here. I'm happy to pass this around. People can look at it during class or after class is fine. Certainly any problem that you got wrong, I don't want you to just take this quest and throw it in a folder and never look at it. I want you to learn how to do it right. So answer key might help with that. I'll just put it here, and if it goes around, that's fine. So that is that. I have reprinted the calendar because the snow day pushed everything down another day. So make sure you grab a copy of the calendar. They're on the table. Everybody have a copy of the new calendar? We have them in the back? Thank you, Dave. Okay, so if you take a look at the calendar here, we're on class 13, and over the next 4 classes, you see that we are in the same 2 sections over and over and over again. Today we'll talk about section 2.1, which is solving systems of equations graphically, and the next 3 days we talk about solving systems algebraically, and in particular 2 days on applications. What does applications really mean to you? What does applications mean? Yeah, how something applies, yeah. Word problems, right? This is what we're going to be spending those 2 days on. Lots and lots of word problems. So today we talk about solving systems of equations graphically. It's a ways away, but our first test is on Wednesday, March the 13th. So we've got about 2 weeks until that happens, but it will be here before we know it. That's our first test. The difference between the quest and the test is that the test is on everything for the semester, and the quest was only on, the last 4 or 5 classes, okay? So it is not too early, even though the test is a week and a half away, it's not too early to go back and start reviewing some of the stuff from the first quest, or reviewing some of the stuff from the quest that we've just seen, okay? Any questions on the calendar? All right, so a little bit more about the calendar. I have no office hours today right after class. I apologize. I'm on a committee and we have meetings this afternoon and then a few other afternoons. I've written them here on the board. I'm always available on Fridays right before class for half an hour. The meeting times couldn't be changed, so I apologize that they are conflicting with my office hours, but certainly I'm available outside of the normal Friday afternoon slot. So if you have questions, just let me know. We will pick a time that works for everybody, okay? The other thing is, and this is a little ways away, but on the day of this test, I cannot be here. I'm going to have somebody else covering. Another math teacher will be here administering that exam on March 13th. And actually on March 15th as well, I'm also going to be out of town. I'll be at a conference on those 2 days. I'll have somebody else, another math teacher, come in and teach that day. So we're not missing any classes, but just a little bit of advance warning. I will not be here on those 2 days. Okay. So if we open to page 57, that's where we start the new material for today. And on page 57, we dive into this new idea of systems of equations. So systems of equations, anybody know this phrase? What does it mean to have a system of equations?
Perhaps a group of equations.
A group of equations. That's it. All we're going to be doing here is solving 2 equations at the same time. So we're going to motivate that with an example, but at its heart, all we're doing now is solving 2 equations at the same time. So let's jump down to number 2, and we'll go to Dave. Can you read number 2, please? Okay, let's take a look at the chart here. So we've got the first company, which charges a flat rate of 30 cents a mile. Right, we're renting a car, so however many miles we drive will affect the cost. And then there's a fixed charge of $0 per day. So it's just 30 cents a mile. That's what you pay, right? In the second example, what do you think about the mileage rate? This is better, 10 cents a mile instead of 30 cents a mile, yes? So just looking at that column, rental company B is cheaper for us. However, rental company B has this fixed charge of $20. So as soon as you walk in the door, you got to pay 20 bucks. And only then do you start paying the discounted mileage rate. So which one should you pick? Perfect. Everybody hear what Sam just said? It depends on how far you're driving. If you drive not very far, I want you guys to either point a thumbs up if you think the top row is better, or a thumbs down if the bottom row is better. If you drive not very far, which row is better? Top one or the bottom one? Waiting for a few more votes. If you drive not very far. All right, so most of the votes that I see are the thumbs up, this top row. That sounds good to me. If you drive not very far, yes, you're paying more mileage than in the bottom one, but you don't have any fixed costs that you have to make up for. So if you drive not very far, the top row is better. But if you're going to drive down to Florida, then it feels like the $20 will get absorbed pretty early on in our trip, and then for the rest of for the rest of the trip, we're paying this lower rate, and I think the bottom row would be better if we drive really far. So what do you think the question is that we're going to ask here?
If the car drives X miles.
Yeah, we're going to figure out exactly when the first row becomes not as good as the second row. Sometimes the first row is the winner, sometimes the second row is the winner. We're going to find the place where they're equal to each other. Okay, so let's go down here to part A, and we'll go to Evan.
Write a linear equation for each rental company that expresses the total daily cost of Y, renting a car and driving Y a fixed cost.
Okay, so let's fill this in here. So first of all, just get used to the letters. X is the number of miles that we're driving. Y is the cost to us. And we're just putting these little subscripts on here, the A and the B, to differentiate the company A from company B. So company A is the top row. It's 30 cents a mile. How do I bring the X into play here? Michelle? I'm going to stick an extra 0 there, but we don't need it. What Michelle said is perfect. But 0.30 X, buy it. 30 cents a mile, 0.30 times X. How did the fixed costs come into this equation? Yeah, it should, technically it's a plus 0. And again, you don't need to write it, but it's adding in the fixed costs that are over there. So if you believe that, then you should be able to figure out what the bottom row equation is. So go ahead and write an equation for the bottom row. All right, somebody we haven't heard from yet. What's the equation down here? Yeah, Tenzin. Point what X? X. Everybody buy it? So these are our two equations. And so what we're going to do is graph these two equations. So how about we go down, I guess it's on the next page actually. We're going to skip some, there's a lot of language stuff happening. We can come back and look at the language, but I just want to get to the heart of this problem, which is graphing those two lines. Now the fact is you could graph them relatively quickly. I want a very, very accurate graph here. If we have an inaccurate graph, then what we're about to do to solve the problem isn't going to work. So we want to be really accurate. So I'll write down the two equations again up here. So y sub a was 0.30x plus nothing, and then y sub b was 0.10x plus 20. So can you guys split up the work? Some of you can fill in the first column, the first table, and some people can fill in the second table. Split that up on in your groups. Make sure everybody's doing something, and then just grab the answers from each other. When you're done, plot all the points and draw some straight lines with a straight edge if you have one. All right. Any questions about the table? Everybody's all right filling in the numbers in the tables? And then we plot the points, and we get these two different lines. And hopefully you can see from the pictures that in the beginning, one of them is better than the other. Which one is better if you're going to drive 10 miles? The green one is better, because if you're on the green one, then you're paying like $4 or something like that. But if you're on the other plan, you're up there at 22 because you paid that initial $20 and you haven't made up the difference. Yeah, you're not paying very much per mile, but you're only driving 10 miles and you don't have a chance to make up for the extra $20 that you just put out of pocket in the beginning. Why is the green one steeper than the black one? You're paying more per mile. That's exactly what the slope of that line is. The slope of this green line, the first equation up here, what's the slope of that line? 0.30. It's steeper than the slope over here. What's the slope of that line? 0.10. So the green one is steeper, but it starts out below. So eventually it catches up and then passes the black line, And actually, we happened to find the point where they were equal because I happened to pick it in the table. What was the point where they were equal? Was it 100 miles? If you're driving 100 miles, how much does company A charge you? 30. And how much does company B charge you? Also 30. So if you're driving exactly 100 miles, which one should you pick? Either one. It's 30. 30 bucks is what you pay no matter what. But if you're driving less than 100 miles, then which one is better? A, the green one. If you're driving more than 100 miles, which one is better? Is B, the black line up here. So 100 is the break even, the one where they're equal to each other. And so that point right there is what we're going to call the solution to the system of equations. It's x equals 100 and y equals 30. So system of equations, as Evan just says, is more than one equation. For us, we're going to be solving two equations. That's what we're doing here. And the solution is the point that's on both. It's the point of intersection. And sure, we could have just looked at the table because we got lucky here. 100, 30 was in both tables, right? But even if we hadn't plotted the points 130 for either line, I'm hoping that you could still look at the picture and say, oh, where do these lines intersect? Can you look at it and estimate where they intersect? You can. If you have a decent graph, you say, oh, it's right there. Looks like it's approximately 100 and approximately 30. And that's all we're after is an approximate answer to this problem. Anytime you're graphing, you're approximating. So we'll come down here. I think we'll just rewrite the equations in this part. So what were our two equations? It was 0.30x plus nothing, and then a 0.10x plus 20. And then we'll jump out down here to part H. Drew, could you read part H for us? Okay, so our solution is x equals 100, y equals 30, or if you want to write it as an ordered pair, that's fine too. All right, let me ask you this. Suppose that I say that x is equal to, let's do a number that we've already done, 20. X is 20 and y is 6. If you plug 20 and 6 into this first equation, is the equation true? X is 20, 20 times 0.30 is 6. The equation's true. If you plug 20 and 6 into this equation, is it true? It's not. And you can double check the arithmetic, but if you plug 20 in fact, you did plug 20 into that other equation, and you got 22, right? Oops, undo. So what we didn't get, I lost where we are here. Here we are. So we didn't get 6 when we plugged 20 into the second equation. So 20, 6, it satisfies the one equation, but it doesn't satisfy the other equation. If we tried, for example, x is 140 and y is 34, look at your two tables. That satisfies one of the equations. Which one does that satisfy? Is B. Company B satisfies this point satisfies company B's equation. So this one works here. Does 140 give you 34 in the other equation? No, it gave us some other number. It gave us 42. So 140, 34 satisfies the second equation, but not the first. What's special about 100, 30? It works for both. 100, 30 is the one set of numbers that makes both equations true. There are plenty of points that make the first equation true. Up in your table, you found 5 of them. There are plenty of points that make the first equation true. Any point that's on this black line, any point that's on the green line makes the first equation true. And there are also plenty of points that make company B work. Any point on the black line works, but there's only one point that makes them true at the same time. And that's what we mean when we say find the solution to the system of equations, is find the point that makes them both true simultaneously. Evan.
Are we ever going to see an equation that has?
That's a great question. Suppose that, so everything we've played around with so far in terms of graphing has been lines. So suppose that you draw two lines. In this case, how many times did those two lines hit each other? Just the once. Is it possible to have two lines hit each other exactly twice? No. Just about any two lines you draw, they're going to hit each other exactly once, like this picture. Now, there are some special cases, and we'll see them, but because Evan's bringing it up, is it possible for two lines to not hit each other once? What kind of lines? Parallel lines wouldn't hit each other at all. How many solutions would you say you have when you have two parallel lines? None. There are no points that are on both lines at the same time. Is it possible, this is kind of a trick question, is it possible for two lines to have more than one solution? How? If they're exactly the same line. It's kind of cheesy, but if you drew the same line twice, then any point on the line is on both lines automatically. So in that case, how many solutions would it have? Infinitely many, any point. We'll see that. But those are special. Almost all the time, Evan, it's exactly one solution. Okay. All right, so on the next page, we'll go to number 3. Davis?
You can see the common general order.
Okay, so there's a lot of vocabulary here. I apologize to throw this much vocabulary into one sentence, but solution we're talking about now is the point that's on both equations. It's on both lines, satisfies both equations, I should say. A system, Evan just says, means more than one. In our case, we're going to be looking at two every single time. Linear equations, okay, linear equations, so that's like our mx plus b thing. And every equation we're going to look at today is going to look like mx plus b in some form. There are other kinds of equations out there. For example, later on we'll talk about graphing an x squared. It's not a straight line. Some of you maybe already know what that is. We'll talk about it. But anyway, linear just means we're going to see mx plus b as opposed to something with a squared in it. The two variables, we don't really need to add this vocabulary, but for example, 3x minus 1 equals 4 is technically a linear equation, but it has how many variables? Just one. It's a single dot. There's no line there. It's just a single point. So this is my way of just saying we're going to have x and y in every one of our equations. Okay, so let's go down to number 4, and we're around to Katrina. Okay, so we've got these two equations. And going through the whole process of graphing them is a long process, and we're going to do it again. But figuring out if a given point is a solution is a short process, and I want to make sure you can do that process. So all we're saying is that if you plug in x equals -3 and y equals 1, are these equations true or are they false? That's all we're after. So let's go ahead and plug into the first equation. Instead of x, what are we putting? -3 minus y, minus. How much is y? Is 1. I'm going to put equals with a big old question mark on the top because I don't know if it's equal or not. -4. Is it true? Yes. So this is true. Go ahead and do the same thing in the other equation. Just replace the x and the y with those same two numbers and decide whether it's equal or not. Is that a true statement? Yes, it is. So right there, we have -3, 1. Is it a solution? Yes, because it made both statements true. If they were both false, would it have been a solution? No. If one of them was true, but the other one was false, would it be a solution? No, this is the only case where the answer is yes, it is a solution. Both true statements. That point right there lies on two different lines. It's the intersection point. Right? So without even seeing the specific picture, in your mind, you can still visualize the first equation is one line, second equation is another line. Apparently -3, 1 is where they hit each other. That's the solution. Any questions on what it means to be a solution? Okay, can we go to Aaron for the note? Everybody understand the difference between finding the solution as opposed to verifying whether or not something given to you is a solution? One problem's short, it's easy, it's the one we just did. That's the verifying. Number 5 is the long process. Let's go through it. We'll go back to Dan in the back, number 5. Okay, so let's see if we can do this one a little bit quicker than the rental car example. So we've got the two equations. Your job is to just graph these two equations. So I'm going to make a little table here. And if it's a line, how many points do we need? Just 2. All we need is 2 points, and then we'll connect the dots. For me, if x's and y's are both on the same side of the equation like they are here, I know a lot of us have a default of solve for what letter every time? To solve for y every time. Some people just say, I want to solve for y, so it looks like y equals mx plus b. You don't need to do that. Depends on what the question says. But for me, every single time the x and y are together on the same side, I'm doing the intercepts. They're very easy to find. So if x is 0, you can just put your finger over the x. It's nothing. 2y equals 4. How much is y? It's 2. So with very little effort, we get to put a 2 there. In the second row, y is equal to 0. So with your finger, cross that term out because it's nothing. How much is x? It's 4. You just read it. It's really easy to find 2 points like this. And I hope you remember doing stuff like that a few weeks back. So plot those 2 points. And with a straight edge, it's important to use a straight edge if you have one. You can use the folder that's on the table. Because how accurate your final answer is depends entirely on how well you draw these points. We don't have folders. Of course you don't. Okay, so here are the folders that you can use. Or a book or your calculator. Very carefully draw those 2 points and then connect the dots. Okay, so we've got our first line drawn. Everybody good? Okay, next thing to do is to find 2 points that are on the other line. This one is not as nice. This one, to be honest, I probably would solve for y. It's pretty easy to solve for y. So if I subtract 3 from both sides, I get that. And so just for practice, I'm going to graph this line in a different way than I graphed the first one. I'm not going to make a table, but I want to see if we're still comfortable with the different ways to draw lines. What is the y-intercept of that line? Is -3. Plot that point. It's a point. Find it. The y-intercept there is -3. Okay, so 0, -3 is down here. That's the y-intercept. What's the slope of this line?
2.
So the slope of this line is the number touching the x. So the slope in this case is 2, which I'm going to force to be a fraction by writing it as 2 over 1. And then I'm going to think of this as my rise and my run. So This is a different way to draw the line. You start at a point. You got to have a point to start with. For me, it's the y-intercept. It's drawn in green. From that point, I'm supposed to rise 2, positive 2, and run positive 1. So rising 2 brings me to there, but don't put a dot there. That's a temporary spot. And then we run 1, which means which way? To the right. That's a positive 1 in the x direction. So you run positive 1 in the x, and you land right there. And we'll do it again. From this new point, I'll do it. The rise is a positive 2. That's positive 2 up. The run is a positive 1. And the positive in the x direction is to the right. So from this point, you can go up 2, rising 2, and then over 1. 2 points is enough, but there's 3. And then again with a straight edge, go ahead and connect the dots. And then once you got the 2 lines, the slope is 2 because we solved this equation right here for y by subtracting the 3, and that gives me this. So the slope is the number touching the x. So I'll walk around for the questions on this, but if you've got a good picture, go ahead and write down what the solution is. Solution is 2 numbers, an x and a y.
Something, yeah, it's you taking the x and you take this one.
Oh, perpendicular? Oh, good question. Good question. So there's a question about these 2 lines. And this question, you don't need to answer this question to figure out the answer to the problem we're given, but the 2 lines kind of look special. What kind of looks special about the way it looks like maybe they're perpendicular. There's no way to just look at the picture and know, but the equations tell you everything you need to know. You guys remember that perpendicular has to do with what characteristic of a line? The slope. So the question is, what's the slope? So on the one hand, the slope is 2. We did that already. What we didn't do over here is find the slope. So you can either calculate the slope by using the 2 points that you have, or you could solve for y. Probably easier just to calculate the slope from the point. So let's do that. So if we calculate the slope here, change in y over change in x, what do we have? 2 minus 0 over 0 minus 4. 2 over negative 4 is negative 1/2, which is the negative reciprocal. So they are exactly perpendicular. Good catch, Septap. So the question we were presented with here was, what is the solution to the system of equations? And all you're doing is looking for the point of intersection. It looks like it's right in there. So you do your best to estimate that point. What comma what? 2 comma 1. Or x equals 2, y equals 1. That's the solution. That's the final answer to all these questions. All of these questions. Any questions on that? Okay, so I think we've already talked about number 6, but let's fill it in now. If the graphs of a system are intersecting lines, how many solutions will the system have? Just 1. If they intersect exactly once, which is how most lines are, then you will have 1 solution. If the graphs are not intersecting lines, and that must mean they never hit each other, and it's none, no solutions. 2 parallel lines. So if they're the same line, then I can't say they don't intersect. They intersect quite often if they're the same line. But you're right, that is the third case. It's just not here. Okay, on the next page, 3 different possibilities. So how about we do this a little bit quick? I trust that you guys are now good at graphing equations, so we're just gonna do this real fast. If you just want to wait around for the lines and then draw the lines at the end, that's okay. If y is equal to 0 in this equation, how much is x? 3. If x is equal to 0, how much is y? 3. So I have 2 points there and there. That's my line. What you're drawing here doesn't have to be very accurate. And we're going to just draw these quick because all we're after is how the lines interact with each other. Okay, in the next one, if x is 0, how much is y? It's -7. If y is 0, how much is x? It's +7. So I'm going to draw the 2 points. X was +7, y was -7. So those are my 2 points. And we connect the dots. Okay, and again, how many points, how many solutions do we have here? Just one. One solution. And I'm not so worried about grabbing it. I wasn't very accurate when I did mine. I want to make sure there's time to do this group thing coming up, so that's enough for that problem. How about this next problem? Y equals 2x minus 5. What's the y-intercept? -5. What's the slope? Slope is just a number, so just the 2 part. So just draw something that is fairly steep uphill. Again, I'm not being very accurate right now. But let's look at the other line. What's the y-intercept? It's 4. What's the slope? What's the slope of the second line? Is 2. Same slope. So same steepness. So I'm going to draw something with the same steepness. So how many solutions does this system have? There's none. No solutions. All right, and the next one is the sneaky one. So again, we'll do this kind of quick. But if y is equal to 0, how much is x?
3.
It's 3. If x is equal to 0, how much is y?
3.
Also 3. So I've got my 2 different points. X is 3 and y is nothing. Y is 3 and x is nothing. So 2 points. And this line goes downhill. And here's the trick for this last one, is that if you let y equal 0, now how much is x? Is still 3. Okay, no problem. If you let x equal 0, how much is y? Also 3. So then I will draw in green the same exact 2 points.
Infinity.
Right, which leads to the same exact line. So those 2 equations are exactly the same thing. So then we'll say infinitely many solutions. Okay, so I know we graphed the lines quickly, so you can double check the details later on if you want to. But what I wanted to convey with these 3 examples is all the different possibilities when you draw 2 lines. Most times it looks like the first picture. How many solutions? Just one. Rarely does it look like either of the other pictures, but you need to be prepared for it when you see it. In the first case, parallel and different lines. How many solutions? None. In the second and last case, parallel but exactly the same line. How many solutions? Infinitely many, right? Lots of points are on both lines at the same time, as opposed to over here, that's the only point that's on both lines at the same time. Here's some vocabulary. If it looks like the first picture, we call it consistent. If it looks like the second picture, we call it inconsistent. On the one hand, there's a solution. It's consistent. On the other hand, there's no solutions. There's no way to make both of these things true at the same time. So we say that is inconsistent. And then finally, one more word, dependent, because the second line depends on the first line. If I take the first equation right up here and I multiply everything by 3, which is okay, right? Multiply both sides by 3, that's legal. What do you get? You get the second equation. The second equation depends on the first one, right? It is built from the first one. So that's why we call it dependent. Any questions on the vocabulary? Okay, so how about we jump to next page, and actually 2 pages down the road, there's the group activity. So go ahead and jump to page 62, and we have 27 minutes. Let's see if that's enough time to finish this group activity. Group activity.